In this video, I will be talking about trajectory error in more detail than what was covered in the basic HYSPLIT tutorial. Before proceeding, you should review the sections on errors resulting from the computational approach, the use of different meteorological data, and in particular, the suggested approach of multiple trajectories and ensembles to infer the errors that might be associated with any one trajectory due to the undersampling that is inevitable when a continuous field, such as the winds, are represented by discrete data points. I will be discussing a new program that creates a sinusoidal wind field and computes the analytic solution, the true trajectory for that wind field. This result can then be compared to a trajectory computed with HYSPLIT using a data file containing the gridded equivalent of that sinusoidal wind field. One takeaway from the basic tutorial is that the trajectory errors in numerical models, such as HYSPLIT, are primarily due to the use of discrete meteorological data and the typical undersampling of the continuous wind field represented by those data. That is, the winds are defined at points in space and time rather than as a continuous field, resulting in the potential accumulation of errors as the trajectory is integrated in time. There is nothing new or novel about this interpretation. Lester Makta, the former director of NOAA's Air Resources Laboratory, in an unpublished manuscript from 1958, compared analytic solutions of the trajectory equation for various idealized flows with their graphical counterparts to determine the best manual integration approach to use. The graphical approach of the 1950s has been replaced by the digitized integration used in HYSPLIT and other similar numerical models. So at this point, it should be obvious that the analytic approach could also be used to evaluate current numerical methods. By rewriting some of the software provided with the HYSPLIT distribution, I created a new program, which is called winmake, where, following one of Makta's configurations, as shown in equation 39, you can define a wind field with a constant west to east component and a sinusoidal varying south to north component. The program will then compute the analytic solution to the trajectory and output the results to a file compatible with the HYSPLIT trajectory plotting program. The second part of winmake lets you define the spatial and temporal resolution of the meteorological data grid, and then it outputs the results of that wind field to a HYSPLIT compatible file. To be able to run HYSPLIT on these data, the same winds were output at three pressure levels, 1,000, 850, and 700 hectopascals. Example HYSPLIT and analytic trajectories with no vertical motion were computed at 850 hectopascals and are shown in this example, details of which will be discussed in the next section. Standard atmosphere definitions were used for the temperature and height variables. The nature of the functional form for the V component means that U is the same everywhere and V only varies in X and is the same for all Y. At this stage, a practical demonstration is best. The winmake program can be downloaded from GitHub, and to simplify the link with HYSPLIT, place it in the HYSPLIT exec directory. Then from the working directory, type winmake. First enter the zonal U component, the west to east wind speed, in meters per second. Note that this entry, as well as all other entries, have a default value. If the default has a decimal point, enter your value with a decimal point. If not, then none is needed. Also, if you want to accept the default, just enter a / followed by the return key. The next entry is the maximum amplitude of the V component, the south to north speed, the one with the sinusoidal variation, also in meters per second. For this example, accept the defaults for all entries. The wavelength represents the distance in kilometers over which the V component varies as a sine function from 0 through 1, 0, -1, and finally 0 again, through a complete sine wave. At 1 and -1, V would equal the maximum amplitude. The next entry, the wave speed in kilometers per hour, determines if the wave is stationary or not. For this example, it will be time invariant, that is stationary. Enter 0. The duration of the trajectory calculation determines not just the length of the trajectory, but also the duration of the gridded meteorological data output file. Given the default wind speed, 28 hours is sufficient for the trajectory to go through one wave cycle. For this and all other examples, the true trajectory endpoint positions will be output every 60 minutes. Changing the interval does not change the accuracy, just the fidelity of any subsequent graphics. The last entry of this section is the trajectory starting position within the sine wave, and it is defined by degrees from 0 through 360. At 90 degrees, the V component will be at its maximum value, and the initial trajectory will start off to the northeast, with U equal to 1 and V equal to 2 meters per second. After this last entry, two output files have been created. The windtraj.txt file, which contains the hourly endpoint positions of the analytic trajectory solution in the HYSPLIT trajectory plot format. The second file is the suggested control file for the HYSPLIT simulation that would correspond with the analytic trajectory. The key to making the connection between the two approaches is to translate the starting trajectory position along the sine wave into the latitude-longitude required for the HYSPLIT calculations. This conversion is simplified by assuming that the analytic solution coordinates of x equals y equals 0 corresponds to the HYSPLIT coordinates of latitude equals longitude equals 0, and at the equator, distance in longitude is equivalent to distance in latitude. At 1 degree north or south, this assumption would only be off by 0.02%, essentially the difference between the cosines of 0 and 1 degree. Back to the winmake program. The next section defines the meteorological grid extent in terms of the number of wavelengths. Recall from a previous entry that the wavelength was 100 kilometers. Therefore, if the multiplier is 2, the west to east domain of the grid will be 200 kilometers. The next entry is the spacing of the grid points in kilometers. A 5-kilometer spacing over 200 kilometers results in 40 grid points in both X and Y. For simplicity, all grids are square. With a 60-minute output interval, the output grid will contain the meteorological fields for 29 time periods, all the same because the wave speed was 0, a field for the initial hour plus an additional 28 hours. These data are then written to the HYSPLIT compatible meteorological data file called wingrid.bin. We will examine this file in more detail shortly. In subsequent sections, all these previous inputs will not be discussed in the same level of detail again. After winmake completes, we have the analytic true trajectory, the file wintraj.txt, and the corresponding wind field for that trajectory in the HYSPLIT binary data format, the file wingrid.bin. Open the HYSPLIT graphical user interface, the trajectory setup menu, and retrieve the control file created by the winmake program. Save, and now run model. Open the trajectory display menu, and to the end of the input endpoints file, HYSPLIT, add plus wintraj.txt, the analytic results. Set the time label to hourly, and the display results show two sine wave-like trajectories superimposed on each other. The red is the HYSPLIT trajectory. The first file is always red, while the blue one represents the true trajectory, the analytic solution for the wind field. They are identical. There is no error in the HYSPLIT numeric solution. Just to clarify some of the details in the previous steps, we can use the HYSPLIT utility programs to examine the meteorological data in more detail. For instance, open the Meteorology, Display Data, Grid Domain menu, and set the name of the input file to wingrid.bin. With a grid point plotting interval of 1 and a latitude-longitude display interval of 0.2, the resulting map shows 40 grid points superimposed on the latitude-longitude lines, where the Greenwich meridian is located along the left edge. Only positive starting longitudes are considered when winmake creates these data files. The gridinfo.txt file gives the latitude-longitude values of the lower left, the 1,1 point, and the upper right grid corners at 40/40. Another valuable program can be found in Display Data, Contour Map. Again, enter the wingrid.bin data file, set level to 3, the 850 hectopascal level, and select VECT, the wind vector variable. Although the output file is hourly, set the time increment to 6 hours to limit the number of frames generated by the program. Run the contour program. Once the calculation completes, advancing through time, you can see that the wind field does not change. Also, you can see the two complete wavelengths over the domain. Remember, the starting location was set to 90 degrees, which was converted to 0.22 degrees longitude. This is the location where the wind vector at that longitude shows the maximum V component. Because the wind field is time invariant, the resulting trajectory is sinusoidal. Also, U is the same for all Y. Therefore, the trajectory would be the same for any starting latitude. The last program is Display Data Text Profile. Again, enter the windgrid.bin file. There is no need to examine multiple time periods, as they are all the same. But the output defaults at the grid center when the latitude and longitude entries are 0. To find the results at 0 longitude, just enter a nominal value, say 0.1 for latitude, because the winds at all latitudes are the same. Then run Profile. The results show a west wind where the U component is 1 and the V component is 0, as defined by the sinusoidal V component function. Vertical velocity is 0, and the three data levels are defined by temperature and height variations according to the standard atmosphere. These data are sufficient to compute trajectories using HYSPLIT. To get a better understanding of the trajectory computation and its relation to the wind field, instead of assuming that the sinusoidal wave of the V component is stationary, set it equal to the zonal wind speed. Rerun the winmake program, leave all input values with their defaults, except the wave speed, which at 3.6 kilometers per hour would equal the default zonal wind speed of 1 meter per second. I'm not going to show the individual steps for winmake in HYSPLIT again, but the resulting trajectory for the 90-degree starting location shows a straight line to the northeast for both the analytic and numeric solutions. The initial wind field is the same as before in the stationary example. But using the contour utility, you can see now how it shifts to the east with time. The location of the maximum V component shifts in time to correspond with each new trajectory endpoint position. The trajectory endpoints always match the location of the maximum V component, resulting in the straight line trajectory. Let's do this again. Instead of starting at the location of the V maximum, start where V is equal to 0. Rerun winmake with a starting location of 0 degrees and again a wave speed of 3.6 kilometers per hour. Before running HYSPLIT, remember to reload the control file because the starting location has changed. The computational result is another straight trajectory, but this time from west to east. The point of this exercise was to demonstrate that it is not just the wind field that determines the trajectory, but also how that field changes with time. Reassuringly, in both cases, the analytic and numerical solutions were identical. Now we have a sufficient grasp of the computational tools to get to the central issue: the effects of decreasing spatial resolution on the accuracy of the numerical integration of the trajectory position. Recall that the base case shown previously, using all the defaults, a stationary wind field with a 5-kilometer grid resolution, essentially showed no trajectory error. Now go ahead and rerun winmake with all the defaults, except increase the grid size from 5 to 20 kilometers. And then when complete, reload the control file, as the starting position has changed from the previous simulation. Run HYSPLIT, and after you display the two trajectories, you can see that although there are some errors, they have canceled each other out at the final 28-hour position. Continue this sequence of calculations using increasingly coarser grid resolutions of 40, 60, and 80 kilometers. The control file does not have to be reloaded with each simulation, as the starting position is unchanged. You can see how the errors increased, which may or may not be compensated by the end of the calculation. Clearly, at 80-kilometer resolution, close to the wavelength of the wind field, the trajectory error systematically increases with time. As in all examples, blue is the true analytic solution, while red is the HYSPLIT numerical integration using the discrete data fields. Errors occur not just due to undersampling in space, but also in time. To show these effects, the wind field also needs to change with time. So instead of the default of a stationary wind field, rerun winmake and define a wave motion to be slightly faster, say 5 kilometers per hour, than the zonal wind speed of 1 meter per second or 3.6 kilometers per hour. All other values can remain at their defaults. The resulting trajectory, with a temporal resolution of 1 hour at 5-kilometer spatial resolution, shows a curved trajectory with a slight error around the region of the curve peak. Repeating the calculations with gridded data output intervals of 2 hours and 3 hours shows a small progressive increase in the errors until the 6-hour interval calculation, which shows a much larger error. Meteorological data at intervals of 6 hours is not uncommon for some global and historical data archives. The trajectory error may also change for different starting locations within the wind field wave or with different wave speeds. At this point, one might ask if the winmake program has any practical value beyond its pedantic application. It might be possible to define the sine wave characteristics of the wind field for a small region, but it is quite likely that those values would change over time. Perhaps for well-defined flows, such as a trajectory for a balloon passing through a sharp ridge or trough, one might be able to approximate the potential error in the calculation. The main value of this program is that it provides an opportunity to deconstruct the trajectory calculation into its basic components and to improve one's understanding of how the limits in the meteorological data, in terms of its spatial and temporal resolution, can affect the accuracy of the numerical trajectory integration.